get both. However, which of these will be the major, which of the two organic products is the major product?
2-bromopropane?
So there'll be more of this in the mixture, less of that. So it's not or, it's and. We get both, just more of this, less of that. Make sense, everybody? Yes? Okay, so I think, ask you to write the mechanism for how both are being produced. So let's just to refresh our memories about the mechanism for these reactions. Let's just write it again. The more times you write it, the better you'll remember it. Okay, so let's start with explaining this product, because you can't explain both at the same time. So let's write a mechanism to explain the minor product first. Yeah? So what's the first stage? Initiation stage. What's happening in the initiation stage?
The 2 bromines separate.
The bromine is homolytically breaking to create using the energy from the heat to create what? 2 bromine radicals or 2 bromine atoms in this case, whatever you call it. Sounds okay? Then comes propagation stage. Can someone tell me what's the first step in the propagation stage?
1 radical Br plus HC3CH2CH3.
So the propane, right? Now we are focusing on this product, guys. So when the bromine radical is reacting with propane, which hydrogen is, notice I didn't say proton because it's not a proton. It's a hydrogen atom with 1 electron. Which hydrogen atom is it going to take? The one that is primary or the one that's secondary?
Primary.
Because we are focusing on that product. Isn't that right? So that's a bond made. This is a bond broken. What does that create?
HBr.
Okay, and?
HBr plus a propyl radical.
A primary propyl
Primary
radical.
propyl radical.
Agreed? Second step, what happens? That primary propyl radical is going to do what?
Plus
React with a
Br,
Br2.
bond Br.
And that is bond broken. This is bond created. What's the outcome?
Propane Br plus Br.
Right? Please
Radical.
remember the 4 bullet points for propagation stage. Every step has to use a radical, create a radical. Every step has to show bond breaking and bond making. The sum of all the steps must equal the overall reaction. And what was the 4th one? The chain reaction.
Yeah, it must be in a chain
You're creating
reaction.
something that feeds into this step, which you create something that feeds into the previous step, and it just keeps on and on and on and on. We good, everybody? What stage comes after?
Termination
Then comes the
stage.
termination stage. Termination stage is basically you take all radicals 2 at a time and just pair them without creating any new ones. This is where bonds are being created, not broken. So if 2 of these radicals were to come together, well, they make a bond, but don't break a bond. This is a termination stage, only bonds made. Of course, bromine atoms, 2 of them could, it's all statistically happening in the same pot. So maybe 2 of these will cross paths. If 2 of these cross paths and come together, well, they make that again. And then why isn't it likely for 1 of these to come together with 1 of those, and that will create what?
Hexane.
Hexane. So those fall in the termination. Does that look okay for everybody? So that mechanism is explaining this product. What if we needed to write a mechanism, and the question will be specific. Question will say, write a mechanism for this product, or write a mechanism for that product. Okay, what if the question were like, write a mechanism for the major product? Will this change?
No.
No. What will change?
Secondary hydrogen
So,
gets
exactly.
replaced.
This is not the hydrogen that is going to be taken to make the major product. It's one of the secondary hydrogens, so that you create a secondary radical. Isn't that right? And it is the secondary radical that is then going to react with bromine to therefore put. Isn't that right? And then, of course, when you're writing the termination stage, you can adjust it accordingly. Does that make sense, everybody?
Yep.
Yes. Of the 3 stages, this is the most important stage. This is where most of the product is being created. So this is the one we really need to focus on. Yes.
I just don't remember what is the difference if you do heat or if you do light.
None. You choose one or the other.
But the process is the same,
The
right?
same,
No, okay.
exactly.
There's nothing.
The purpose of heat and light is to give us the energy needed for this step. Now, energy is going to come from one of those sources. It's your choice. Everything else is the same. No difference.
What about MDS? That was on the
gotten
worksheet.
there yet. We'll get to it. Not. Oops.
Please hold your exam.
Oh, sorry. Did you need that again?
No, just.
Okay. Thank you.
I'll
for
send you a
catching.
picture of that.
NDS is something we'll get to a bit later. We're not there yet.
Thanks.
Yes.
What was each step called again?
I want to say something.
Go for it.
Go for it. Really?
Yeah.
You were enjoying sunshine in Hawaii.
So yeah.
You don't have a right to ask questions for Monday's missed class.
It was wonderful.
Initiation. Where was that? Initiation. Where you're initiating the process. Propagation. Where the process is propagating. And termination. Okay. Guys, are we good?
Yes.
Please practice writing these mechanisms. It's, as I've said already, it's muscle memory. Can I erase this part now?
Yeah.
Okay, it's just that I'm lazy to go over there.
So
Good. Yes, go ahead.
So this will be on for
Quiz.
next week, right?
Monday.
Okay.
Yes.
This will just be. Is this going to be the only thing that's going to be on the quiz, or with?
No, we are doing some stuff today too.
Okay.
hmm
Yeah.
And we did some stuff yesterday also.
Yesterday was lab.
Oh, no,
Monday.
Monday, yes.
Okay, so here is a question for you. Question. Do you guys remember this word? We used this word on Monday.
Yes.
Right? You guys remember that word, regioisomeric?
Yep.
Perfect. 2, for people who were having a great time in Hawaii,
Mm-hmm.
well, we were struggling with rain and
I got
misery.
sunburned.
Yeah.
Oh, I feel
In
so
Hawaii.
sorry for you.
Not the same. Regioisomer is the same as constitutional isomer. It's another word. Same thing, constitutional isomer, regioisomer, structural isomer, same. Okay, so those are the questions that you need to answer for the structures that I'm going to draw. Okay. By the way, what kind of compounds, which compounds go through this reaction? Which family of compounds go through this reaction? Which family of compounds can be halogenate,
Alkanes.
alkanes, or
Alkyls.
not alkenes?
Alkyl?
Alkyl is a
Alcohol.
group, not alcohol, we're not there yet.
Allele?
Just this reaction, this reaction. Okay, alkanes or cycloalkanes, because, right, it's just alkanes is cyclic, because it's the hydrogen on the sp3 atom that is being substituted. So alkanes or cycloalkanes. Okay, so let's do this. A. And we are only talking about monohalogenation. We are not interested in polyhalogenation. That's not our focus. Okay. Please go ahead. Here are 3 alkanes or cycloalkanes. You got to tell me question 1, question 2, question 3. Please, let's do this quicker. Faster. So what do you say for question number 1 for A? Is there an easier way to answer question 1?
Yeah.
Which is what? Which is what?
Count the number of different hydrogens and it's 2 to that
Exactly.
number.
Yeah, different H's.
Exactly. The number of hydrogen types is equal to the number of regioisomeric products you'll get. So how many types of hydrogen does this molecule have?
2.
Careful.
Um,
Think NMR. Think proton NMR. If you were doing a proton NMR on this, how many proton signals will you see?
4.
4.
mhm.
There are 4 types of hydrogens here. So therefore there are 4 products. 4 monohalogenated regioisomeric products. Do you all see that? Those are not identical to each other. So this is going to give you 1, 2, 3, and those are identical, so 4. Everybody okay? Let's draw those 4, please. Let's go ahead and draw those 4 products that you can. Yes, go ahead.
You're not, okay, forgot. Not poly, never mind.
No polys, yeah,
Okay.
no polys.
That's why I
So
said
poly
two-
can go in.
That's why I said 2 to them.
Oh, I see. Yeah. Then you're just, what's that phrase? Can of worms, basically. Okay, let's draw out the 4 monohalogenated. We are only talking monohalogenated. So if the halogen, whatever the halogen is, went here, chlorine, bromine, that's 1, right? If the halogen went here, that's another 1, isn't that right? Yes, no?
Yeah.
And if the halogen went there, or the halogen went to one of these methyls. Agreed? 4 structural isomers. By the way, the question might be more specific in the sense chlorination or bromination, so then X is Cl or Br. Make sense? Okay. Then question number 3, identify the major of those 4 products. In your opinion, which of those 4 products is will be the major product? The regioselectivity is the major product comes from the most stable radical intermediate.
In the most stable.
So which one would that be in
The
this case?
tertiary.
Tertiary. So
lily.
where is
One-
that?
the
There's
one-
no lilic here
Yeah.
because there's no double
No,
bond.
no, no.
X,
Which one would that
X,
be?
X with on the same side as the 2 methyls.
That
That
one?
guy.
Absolutely. Oh, thank you so much, Mark. Agreed? Everybody? Yes, no, maybe.
Yeah.
Perfect. Let's go and do that for B and C as well, please. Quickly. Feel free to come up and write your answers, please.
Yeah, I have a question.
Please,
It's
yes.
Probably I just need to review last
No,
quarter's
go ahead.
stuff, but, I'm stuck on my chair. I was just gonna say, sorry, Carter, real quick.
Yeah.
So I know these are identical.
Yes.
And then this is number 2,
Different.
group 2.
Yeah.
Group 3, but how come these are not enantiomers, or do we
Oh,
not care because it's
oh.
regio?
They are,
Like,
yes,
it's structural,
exactly,
not
exactly,
stereoisomers.
exactly. You're absolutely right. Structural isomers,
Okay.
not stereoisomers.
Would those be 2 different hydrogens
They
on
will be,
NMR?
you're absolutely, no, they won't. They're enantiotropic hydrogens. There's no other pre-existing stereoisomer. Let me write it.
Okay.
Let me write it.
I understand it was not a good question.
So,
I understand it was not a good question.
these hydrogens, are these, what's the category of these hydrogens? Are they homotopic, enantiotopic, or diastereotopic?
Enantiotopic?
Do you agree? Because there's no pre-existing stereocenter. If there's no pre-existing stereocenter and I replace one of them with whatever, X, okay, I'm just going to use X, and or replace the other one with X. Sorry. What's the relationship between these two molecules?
They're the same.
Louder?
They're the same.
They're not the same. Not after 261, they cannot be the
They're
same.
different.
Unless you're having Mai Tais in Hawaii. What's the relationship between these two guys?
Are they enantiomers?
They're enantiomers. They're stereoisomers. They're not structural isomers, obviously. They're not regioisomers. Maybe that's what you meant, Dash. They're not structural isomers, but they are stereoisomers. And how many stereocenters? Is that a stereocenter?
No.
No, because it has
No.
2 methyls, so there's only one, absolutely. Can someone tell me if this is R or X? Fine, I'll just make it more specific, let's make it Cl. Is this R or S? Very quickly, guys. Is this one R or S? 1, 2, 3, right? How about this one? Then it should be,
Yes.
they are what? They are enantiomers. If they are enantiomers, that means that these are enantiotopic. So in NMR, you will only get one signal. Homotopic hydrogens give one signal, enantiotopic hydrogens give one signal. It's the diastereotopic hydrogens which can give different signals. Right, so just one signal. However, coming to the other question I think you were asking was, I did not separate the enantiomers because the question was very specific about regioisomers. If the question was show all products, well then, I'll get 2 of those. The others are the same because they are not stereocentered. So yeah, then actually I'm going to get a total of 5 compounds. I'm going to get A, B, C, and 1 enantiomer and the other enantiomer. Absolutely. Okay, please, let's go ahead and you got to answer all. Carter.
I wrote one of my possible answers there.
But that's not right.
Oh.
You lost carbons. You got to count carbons. And don't write one possible answer. Let's answer question 1.
Oh, yes.
Question 2. Question 3.
Oh, yes.
And yeah, count your carbons.
Oh,
I almost did this signal, but I probably.
Rick said she had to put a sign up about counting carbons.
One, two.
Yes.
Would you be able to go over how to find the major product?
The most stable radical creates the major product. Right? You remember that from Monday?
Yeah.
Okay, so most stable radical, and we wrote the order of stability for radicals, gives the major product. That's the regioselectivity for this reaction. Do you remember us doing that? Cool. Do you also have the order of stability in front of you of the different radicals? Methyl radical, less stable than primary radical, less stable than secondary. Well, we wrote it on Monday. Let's write it again. We wrote this on Monday. So, order of stability of radicals. Vinylic and phenyl radicals, meaning those that are on the carbon-carbon double bond or on the benzene ring, are extremely unstable. Extremely. To the point, not formed. They are so unstable that we should never consider them. We will never consider them. So these, of course, not formed. Methyl radical is the least stable primary radical, secondary radical, tertiary radical, and then the most stable ones are allylic and benzylic. One carbon away from benzene, not on the benzene. Do you remember that? Okay, so let's use this for A. Can someone tell me, so if this is the parent alkane, how many radicals is it capable of producing?
4.
Because there are 4 different
There-
hydrogens. Isn't that right?
Yep.
If this hydrogen were taken in the mechanism, and again, you got to be able to write mechanisms, guys. You got to, and that comes with practice, so you got to write it over and over again. So if this hydrogen were taken in the propagation stage, do you agree that that would be the radical created as an intermediate,
Yeah.
right? If this hydrogen were taken in the propagation stage, this would be the radical, yes? If that hydrogen were taken, then, and if one of these were taken because they're identical, agreed? Yes? Of these, which is most stable radical?
Number 3.
That's primary, that's secondary, that's tertiary, that's primary as well. So that's the most stable radical, so the product that comes from here is the major product. Are you seeing it? Yes,
So for B, how
Yes.
would you know which one is more stable since they're both
Oh,
on
shoot.
tertiary?
shoot. Okay, did you say tertiary?
Oh, I keep saying that.
But I think you and I are on the same page. You're right, that's very, very true. I didn't think about that. I think then there will be no selectivity. They will be, at least on paper, they expect it to be equal.
Okay.
So probably 2 major things.
But-
Yeah.
What about the hydrogens that would be on, I'm probably misunderstanding again, but
No, go ahead.
are we talking about this one now?
Yeah.
Like here?
Yes, but major. She was.
Then we have these two,
Uh-huh.
right? So these ones would be primary,
Good.
and these would be secondary.
Good. I think their question is about these.
Okay.
Isn't that right?
Yeah.
And I didn't think about that when I was drawing the structure that, yeah, I mean, there should be 0 selectivity between those two. They should be equally likely because they're both secondary. Yeah. Can I erase this thing? You guys got it? Everybody?
Yeah.
Okay, please, let's go ahead and write the answers for B and C. Let's do this quickly.
We closed that, right?
Yeah.
Okay. Yeah, I'll do it.
Is everyone on the same page right now? Okay. By the way, I don't know if you've noticed, I am actually starting to put the keys for the textbook problems on Canvas for each chapter. So there's no reason to not be practicing. No reason at all. We've got to be practicing. We've got to be putting pen to paper and writing stuff out.
Did I read right for office hours?
Second?
Did I read right for office hours? You also have Monday through Thursday from
9 to
2:30
9:50.
to 3:30.
And Monday only 2:30, not
Oh,
other.
there's something that reads weird.
Monday, Tuesday, Wednesday, Thursday, 9 to 9:50.
And then it says,
Monday, 2:30.
and also 2:30 to 3:30.
Ooh,
And then it says
I should fix
Monday,
that.
and then it says Monday.
Monday, 2:30 to
Yeah,
3:30.
but it does.
Oh,
say
I
that.
should fix that.
Yeah.
Sorry about that. Yes, because
Yeah.
I'm in lab on Tuesdays and Thursdays I'm
Okay.
in lab at that time, and Wednesdays I'm in meetings. So yeah, only Monday. I'll fix that. Thank you. Are you sure?
No. Not that she said that, no.
Am I sure? I agree with your circle. Your circle is absolutely correct.
Is it the 5?
Yeah. That's okay. Let's see what others think. What do you guys think? And please help. No, Jasmine, don't feel bad. We're all processing this, right? If you were to do NMR for this molecule, how many proton signals will it show?
Maybe 4?
Oh, did somebody say 4? Oh, sorry, 4. Yes, 4. No, not 4. Sorry.
5.
Yeah, no.
My brain is not catching up as quickly. But 3. Just 3. Right? Yes. Because these are equivalent. These are equivalent. And here is your third. Look at symmetry. Symmetry. Do you guys agree?
There's, yeah.
Right.
a plan
Also look
symmetry.
at this, if you will. Is there any difference between this product and that? If you were
No.
to name these two compounds, wouldn't they be the same? These are same. What about these two? Same. They are exactly the same things. So only 3 products because there are only 3 types of
I
hydrogens.
see the thing.
And then, so that's, those are the same, these are the same, and here, and yes, that should be the major product because it's coming from a tertiary radical. Do you all agree? Yes. Now B, you're saying 3 products because there are 3 kinds. Again, look, there's symmetry. Means those are identical, these are identical, these are identical. The only thing well, it's actually not a big deal. So, okay, good. And then favored, both of them will be because yes, there's really no selectivity between them. There's no preference for one over the other. Are we all good? Questions? Again, if you are getting at home, when you look at these, write the mechanisms. You got to write those over and over again because that's when it starts sinking in. Okay, I have a couple other questions over there. Let's give it a little time. Here's another way I can ask questions. Hey, what would be the structure of the alkane or cycloalkane that has this chemical formula and can only, guys, the only word is critical here, make 2 monochlorinated products? What would that be? What would be the structure? So go ahead, try it out. Brainstorm, talk to each other, and tell me what the answers will be in the next 2 minutes. I'm just kidding. Take 5. What are the, instead of just looking at the whole forest, can we somehow use the clues to make the choices, the number of choices smaller? Silence. Instead of looking at all things possible, do we have clues here that can reduce our choices?
Yes.
Yes. What's the first clue?
So it's
Symmetry?
likely that one of those carbons has to have 4 bonds because we've got so few options.
4 bonds. They all have to have 4 bonds
Connected to 4 carbons.
connected to 4 carbons. But will it fit C5H10 if you did that? First thing is calculate your IHD, guys. Calculate your IHD. C5H10, what's the IHD? Come
See
on,
if I,
guys, what's the IHD?
1,
1. So is it going to be an alkane? Or is it
no,
going to be a cycloalkane?
yes.
Then that's automatically reduced your choices. Oh, we can't think of an alkane, we got to think of a cycloalkane. Then it's saying that it only can make 2 monochlorinated products. What does that mean? How many types of hydrogens does it have? 2. That's your other clue. A cycloalkane with only 2 types of hydrogens. Go ahead. Clues. Yes. Yes. No, I didn't say alkene. I said alkane or a cycloalkane. That's it. Not the same. Cycloalkane is a cycloalkane with all carbons being sp3 hybridized.
Formula is not.
Formula is the same. I get that, but I'm specifically saying alkane or cycloalkane. Alkene is not included in the choice then. So it has to either be an alkane or a cycloalkane. Go ahead, if you have your answer, please. With obviously 2 types of hydrogens only. Which, by the way, what does that tell us? There are total of 10 hydrogens, but only 2 types.
There
What
are
is-
5.
Constitutional item.
No, that's not what I'm asking. If there are total of 10 hydrogens, but they're all divided into 2 categories only,
There are
what does that indicate?
5 hydrogens.
Symmetry.
5 hydrogens a
Symmetry.
signal. So yeah,
So
there's
you're
symmetry.
thinking about, okay, something cyclic with symmetry so that there are only 2 types of hydrogens. Only 2 types, so because then only you can get 2 products. Say that again? No.
You always had that.
Oh, that's
Could be a bed.
I don't know.
I was thinking either.
things around. You gotta be wrong. Okay, what about this option? What about that option?
Oh, this can't be because this would be the same. So it would have to be this one and this one maybe?
You're dihalogenating it. You can't do that.
Oh no? How do you
You're
2 monochlorinated?
Monochlorinated. You just
just
have one
one.
chlorine on there. Yes.
Okay, so how do you do
How did I do mine?
one there and one here? What's the difference? Right? What's the difference? There's no difference, right?
Count your carbons, right? Ricky, of course, uses an F word in there. I can't use, I come from a generation.
Count your
Don't say
carbons.
the F word.
Count your carbons.
Gotta count your carbons.
So we would get it. So we understand better.
Chlorine goes here or here or here or Again, guys, I've said it before in last quarter, I'll say it, emphasize it again and again and again. The only way to get this is by putting pen to paper and let your brain go. Brainstorm
When heated with CO2.
and practice. That's not important part. The important part is this and this. What's the structure of that? Do you have something, guys? I see a couple of people have it.
I think I have one.
Show me the hand. And are those identical? Yes, exactly. So are they identical? Yeah. That's it, done. Oh, you're working on the diagram? No, but by the way, have you calculated? C8H18? Because then you won't be doing all of this. start with IHD. Whenever there's a chemical formula in front of you, just go and calculate the IHD, because that really does point us.
But
in
how
the
many
right direction.
hydrogens that's got?
What?
How many hydrogens?
Just replace one hydrogen, the Cl.
How
I'm
many
not asking for
hydrogens?
the products, guys. Please understand and read the question carefully. I'm not asking you to tell me what the products are. The question is saying, give the structures of the alkane or cycloalkane, C5H10, that can do the rest. So I need you to give me the structure of the parent alkane or cycloalkane. There's no IHD. Okay, good. Start always with IHD.
Because you need
That tells
10
you, am I looking
10
at a
hydrogen.
cycloalkane or am
Don't
I
you?
looking for an alkane?
10 hydrogen.
Yes.
What's the IHD? Only one part. Oh. What's the IHD of B, the second one, C8H18? Has anybody calculated the IHD?
Isn't it 0?
So then are we looking for an alkane or a cycloalkane if IHD is 0?
And an alkane.
So that's where you should think about. And it can only make one product, which means how many types of hydrogens?
One type.
Yeah, trying to figure out how to draw that in like the.
1, 2, 3,
Okay.
4,
I
5,
need to
6,
move on.
7, 8.
So do it at home, guys.
Oh, I see.
These are the kind of questions that we need to, which only comes with practice. It only comes with practice. So go ahead, spend time on those two at home, and then on Monday tell me what answers you got. But we've got to move on.
This is not going to be on the.
Yes, it can. We've done it. It can. So if you practice, guys, the book
But
has
how are we
similar
gonna-
questions too. If you're, I also have worksheets. So please, it's all about practice. It's not about the 2 hours you spend here. Okay, let's go on to the next topic. Ready?
Yep.
Cool. So, one of the compounds that was on the board for the first, guys, can we go on? The one of the compounds that was on the board earlier, this guy, how many products can it, how many monohalogenated products can it make? 3, right? The major product, I'm only focusing on the major right now. Of course, there are the other 2 minor. And let's say I'm chlorinating it, just as an example. That's the symbol for light. Please remember the energy is coming from light. The major product, do you guys agree, is this? Ooh, wrong, shoot, that doesn't work. Can I just change it slightly so that, there we go. Do you still agree that the major product, ooh, but that's benzylic, this is tertiary. No, not really. Sorry, hold on. But then those become identical. Okay, fine. That is the only thing that I can do. Okay. I had to change it because what I needed to go to was not going to be addressed by the example up there. Do you guys agree that if I had this alkane, the major product would be that?
Yes.
Okay, cool. Now the question is, how many of this product will I get? Of this product. I'm not talking about the others. So what am I asking? How many of this product would I get?
Are you asking about like percent yield?
No, not at all. Don't put words in my question. How many? So again, these are all the different ways people ask. So we need to know, what is she asking? What is she looking for? If I'm focusing on one product and asking how many of this can I get, can I be talking about regioisomers?
Mm-hmm.
Like how
No.
many variations
Oh, no.
of it?
What do you mean by variations of it? That's so generic. What do you mean by that? So, what do you think I'm asking if I'm saying how many of this one product? Exactly. Is that what you were going to say? No. That's okay, but no, why do you have to be honest? Just say, yeah, that's exactly.
Stereo.
Exactly. That's what it's asking. So if it showed one compound, how many? Well, it can't be a structural isomer because it showed only one. So, oh, are they talking about stereoisomers? Is there a stereocenter?
Yes.
Exactly. So therefore, what are they really asking?
How many stereoisomers does it
Which
have?
one? If there is one stereocenter, what kind of stereoisomers would that be? Exactly. So we got to, when questions like these are asked, we got to be able to figure, oh, that's what they want us to say. That's what they're pointing towards. If it's just one compound, then they're not talking about structural isomers, they're talking about stereoisomers, and there's only one stereocenter, which means, okay, that means they're talking about enantiomers. Isn't that right?
Yep.
Yes? So can you draw for me the two enantiomers of that compound? And that should not take us more than a minute, guys. Enantiomers drawing of something that's already there should not take us more than a minute by now because we've done it so much. Done?
Yep, done.
That's all. Keep it simple. Simple. Are we all good? Okay, question. We introduced a word on Monday called regioselectivity, which means selectivity or preference for one regioisomer as over the other regioisomer. Here's another word for us to get really comfortable with, and that is stereoselectivity. What does that mean? What do you think that means?
Prefers one stereoisomer over the other?
Exactly. Preference slash selectivity for one stereoisomer over the other stereoisomer of the same compound. So that's also something that we have to be able to discuss and evaluate as we learn about the reaction. So, in free radical halogenation of a reaction that goes through a free radical intermediate, do we expect one of these to be the major enantiomer, meaning created more in preference to the other? So let's discuss that. You guys ready? Now that has to do with the shape of the intermediate. Can we go back to the shape of the radical? We discussed this on Monday. What is the shape of a carbon radical? If you have a carbon radical, what's the hybrid? Sorry, go ahead.
It's a trigonal planar radical.
Because what's the hybridization state of the carbon that the radical is on?
sp2.
So it is trigonal planar, absolutely. Now please remember the hybrid orbitals make sigma bonds, but what else does this have? Right? Which is where the electron lives. Isn't that right?
Yep.
So now the next step is coming in. And so which side do you think the halogen would prefer to go to? Would the halogen prefer to go to this lobe, or would the halogen prefer to go to this lobe? What do you think? Go with your gut.
Where the electron is?
Well, the electron is just a representation. The electron just doesn't sit in one place. Doesn't the electron, it's an electron cloud. Isn't it? Do you guys remember? It's an electron cloud. It can be anywhere in that area. So will the halogen prefer to go to the top lobe, or will the halogen prefer to go to the bottom lobe of that p orbital to make the new sigma bond? Louder?
The dash or the
On
wedge,
what?
maybe? The dash or the wedge?
Electron cloud, again guys, you're quantifying electron clouds. I think you learned in Gen Chem that there is no such thing. Electrons have equal probability to exist anywhere in that range.
So the dash or the wedge, either one. So,
So which one
which
is
one?
better? Is
the
this better or that better?
Is there a
the
That's the question.
the wedge.
That's the question. Is there a difference?
No
Is
difference.
one more open to take the X compared to the other?
No.
No.
Oh.
No, I don't have the other model kit that I use for that, so I apologize. But imagine, and I know this is not trigonal, but imagine it's trigonal. Just pretend. Here are my hybrid orbitals. Ugh, stay together, right? I know I can't do it. And here is my unhybridized p orbital, which is perpendicular to the hybrid. You get it, right?
Yeah.
So is there any preference for the X to come from the top face or the bottom face?
No.
No.
No. So if this approach is this equally likely compared to this approach, will there be any preference for one of these enantiomers over the other?
No.
No. This reaction does not have stereoselectivity.
Oh.
You will get an equal mixture of both enantiomers. What do we call that, guys? An equal mixture of two
Racemic
enantiomers.
mixture?
Fair. We will get a racemic mixture. That's how racemic mixtures are indicated. You will get the plus enantiomer and the minus enantiomer in equal quantities because the X coming from the top side is equally likely than coming from bottom side, giving us both enantiomers. Do you guys all see that?
Mm-hmm.
Yes? So, regioselectivity depends on the more stable free radical. Stereoselectivity, there is none. There is no stereoselectivity because both enantiomers are equally likely to be formed. So we will get a racemic mixture of that product. Questions so far? Are you guys good so far? Yes? Okay. Then whichever is preferred gives you the major. Absolutely. Now in this case that's not going to happen. Well, artificially I could, artificially maybe I create some alkanes that somehow blocks the top face, then this becomes major because we somehow blocked the top face, or vice versa. So that's more of a special case scenario where we are creating a situation where one face is blocked, so then the other face reacts. Does that answer your question? Yeah? But typically, that's not the case. Okay. Am I ready for that? No, let's do that one. Okay. Here is propene, basically, propene. Maybe this is, let's say I am brominating it. How many products will I get? And again, only monohalogenated. We don't care about polyhalogenation. How many products can I expect that to show? Two. Why? Which two?
The one on the far end, and then the one that has
The
What's the hybridization state?
SP2?
Okay, so do we, in this reaction, do we replace hydrogens on sp2 hybridized carbons or the
No.
hydrogens on sp3?
SP free? Hybridized
Right.
carbons?
Right?
So it would be the carbon at the end.
So how many do we expect? Your answer is though correct, but that's not our expectation, so I'm not going there yet. But so what's our oh, it was Viola, not, I'm staring at Vivian, she must be thinking why she's staring at me. So what is our expected number of products?
2.
2, why 2? Where 2?
Because the SP3 carbon at the end and then the one in the,
But that's sp2. That's
Oh.
sp2.
so just one.
That's our expectation, isn't that right?
Yep.
Everybody agrees?
Yes.
sp3, sp2, sp2. So we expect, oh shoot. Sunita, you don't plan it out well, do you? I'm gonna add a pH there. It's still 2, it's still 1. It's just that, because those are sp2s as well. So do you agree that this would be our expected product? Is that right?
Yes.
Can you write the mechanism? Let's write quickly. That was rhetorical. Go ahead, write the mechanism, please, quickly. So initiation stage, right?
The BR2, the BR,
Go ahead,
the BR2 separates into 2 BR radicals.
write it. Go ahead. Let's go do this fast. Separates, gets 2 BR radicals. Okay. Propagation stage. Step 1. Do you agree? That radical is created, right?
Mm-hmm.
And then of course that radical, once it's created, it can. Okay, termination stage, I'll let you guys write on your own. Termination stage, please do. Let's focus on the propagation stage. Do you agree with the 2 steps in the propagation stage? Right? Is that a yes? Okay.
Yeah.
Yes? Okay. So, I needed us to draw these out so that we can take a look at the free radical intermediate. What kind of free radical intermediate is that? Anybody? It is allylic.
Mm-hmm.
Of course, in this specific case, it's also benzylic, extremely stable because there's also benzene on the other side. But, guys, agreed?
Mm-hmm.
Now, what if I were to say there is one more product? Where is that product coming from? Those carbons are all sp2 hybridized. This is sp2, this is sp2. Where is that product coming from? Anybody? Thoughts? Louder? I think I heard somebody say something.
Is there resonance?
Is there resonance? Are you asking, telling?
Uh,
So there is resonance.
there's
Right?
resonance.
Draw the structure. Exactly. That's why allylic radicals are so stable, because they are stabilized by resonance. So if we draw out the resonance structure, isn't there another radical?
Yep.
You see that? Resonance. Resonance. So this radical is going to resonance delocalized. So can that react instead in step number 2 instead of the other one? Can there be an alternate step number 2 where this radical, because they are resonance structures of each other, this one reacts with bromine and gives us a product? Is that possible?
Yes.
Absolutely, because resonance structures don't exist. What exists is the
Resonance hybrid.
So absolutely there are two products. But the two products are not because there are two kinds of sp3 hybridized carbons. It's because the original radical intermediate can delocalize because of resonance, which creates the other product. So that. Agreed? Everybody okay? Can you tell me which will be major? Which of the two products do you think will be the major product? They're both allylic.
The first one with
This
the
left, sorry.
the left one.
Do you agree?
Closer to phenol than-
Yeah.
Because that's allylic but also secondary and resonance with benzene as well. This one is allylic and resonance with benzene as well, but it's primary. So which radical is more stable? So that gives you the major product. Do you all see that?
Yep.
Everybody? Yes? So please, again, this is all that mechanism thing for this chapter for us to practice over and over again, so you can see, oh yeah, this can resonance delocalize, so then that can happen, so on and so forth. Questions?
No.
So if you understand that without writing the mechanism, can you tell me show me all possible products for
Wouldn't benzene be super stable then?
what happened?
I'm thinking, how is benzene like super not?
Super not what?
What's the word? Stable.
It is. It is very stable. That's why benzene does not react. Okay, maybe that's something that I should address as well. It is very stable. And yes, this will delocalize there as well. In fact, this radical is delocalizing here and in the benzene. It's benzylic as well as allylic. It's extremely stable. But maybe that's a point that I'll mention after this example. But yes, it is very stable. Okay, guys, how many products can you draw for this? Anybody? Did you say I don't understand the question? Is that what you said?
No.
Oh, I don't know. Someone I heard.
I just told Dash I understand his question and I'm still unsure of the.
Oh, okay.
But it's okay, we'll come back.
Sorry, I'm not trying to eavesdrop, but sometimes I hear questions. I'm like, oh yeah, let's talk about this. Let's talk about this. So guys, how many products do you draw there? How many regioisomeric monobrominated products can this create? Anybody? Anyone?
Is it 7?
Okay. Can this form a radical?
Yes,
maybe.
Yes, it can
Can it
form
make
a.
a product?
Yes, that's one
Can
product.
this do the same?
Yeah.
How about this?
Yes.
How about this?
Yes.
How about this?
Yes.
Is there any symmetry to make them equal?
No.
So
No.
what is it? 1, 2, 3, 4, 5?
5 products.
And now, what about this guy?
No,
What
that's
about that guy?
no,
Let's
that's an.
explore. Don't be in a rush. Explore. I'm not going to talk about, actually, even that. Okay. I'm not going to, but if that does, it's the same, so it's, actually more. Okay. Can we just ignore those two because they will do what you expect? Or maybe I'll draw all the radicals. Let's just draw the radicals. Not writing the mechanism. I'm not writing the mechanism here. I'm just drawing the radicals to see what we get. That's one possible, right? Okay, this is another one.
Yep.
This, so I'm just drawing the radicals, no mechanisms here. But of course, you should practice, but Did I miss any radical, did I draw them all? Oops. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Agreed?
Yes.
Okay,
Yeah.
cool. Can this have oh, yes, what?
So what about the double bond?
Again, H comes from an sp3 hybridized carbon atom.
Mm-hmm.
When you write the mechanism, it's the sp3 hybridized carbon atom. Again, I'm not going to write the whole mechanism because we've written it a few times. It goes from an sp3. Oops, not B. To make a radical. So those double bonds are not sp3s. Those are sp2s. Isn't that right? So all I've done is so far, although we're going to elaborate on this a little bit, but what I've done so far, I've just put radical on the sp3 atom so far. You good?
Yep.
Okay. Now the next question is for you to be able to process. Can this do resonance?
Yes.
Because it's a allylic.
The
Okay?
yeah the
Draw out its resonance structure. Please. What would its resonance structure be? Do you agree? Yes?
oh that one. That one.
Can this do resonance?
No.
It's a allylic.
Yes, it
So
can.
the answer is yes. Any carbon next to the double bond is a allylic. Absolutely. What does its resonance structure look like? So if the double bond moved there, you got a radical here. Agreed? Can this do resonance?
No. No.
Everybody agrees? No resonance. Can this do resonance? Can this do resonance?
Yes.
Let's draw its resonance structure. Did I draw these correctly? Yes? Resonance is one of the most important concepts in Ochem. You agree? So now what is the total number of radicals you see? 8.
8 radicals.
1, 2, 3,
Oh.
4, 5, 6, 7, 8.
Mm-hmm.
So how many products?
8 possible products.
Do you guys see that? Everybody.
Mm-hmm.
Of course, I'll let you guys draw the products, the corresponding products for each of those radicals. Please draw it out. I mean, what happens when bromine goes there or there or there, so on and so forth. So there will be 8 products for you to draw. Are we good?
Mm-hmm.
Just by looking at the radicals, is there a way for us to draw the major product in this reaction? Just the major product. If you're looking at all 8 radicals, which of these will give us the major product?
Is it bottom right?
Why?
Because it's
It's tertiary and allylic.
It has free R groups and it's allylic.
Do you guys agree? Most stable radical. So what's the structure of the major product? That's your major product. Does everybody see that? Yes? Cool. So resonance, please don't ignore resonance. If a radical is allylic, yes, it will undergo resonance, which means that yes, both resonance structures can give us the corresponding products. Guys, can I answer any questions here? Yeah, oh, sorry. There's one other question, and it's coming from what you said earlier, Josh, because just to make sure we are all on the same page. How many products possible? How many monochlorinated products possible? Okay, expected. 2. You guys agree? Why? Because we can expect 2 radicals. How many sp3 carbons are there? Two.
Yeah, just those two on
So-
the ethyl
And
group.
remember, hydrogen goes from the sp3 hybridized carbons to make radical. That's one radical. This is not a mechanism, this is not a reaction equation. I'm just showing you the radicals from possible. Agreed? Yes? Which of those radicals is more stable? Why is that more stable than the first? Why?
Because it's
Is that
secondary.
the only reason? Yes, it is
Allylic.
secondary, agreed, but is that the only reason? It's benzylic as well.
It's benz.
So why is benzylic radicals so stable?
So much resonance.
Resonance, same as allylic. The same thing you can do with allylic is because of benzylic. Because obviously then you can draw basically resonance structures and go on and on and on to show how that electron density can be delocalized and so on and so on. I mean, there are more you can draw. Yes?
Okay, all that I understand. What I'm confused about is earlier we were making the rules for stability. There was two that were so.
I'm not saying whether they're not found. One was when a radical was attached to it, like directly on the benzene.
But there's a difference, although, can I finish this before?
Yeah.
We should address that, but let's finish this first. The reason I'm bringing this example here is, yes, of course, there are more structures you can draw, so on and so forth. So, we'll get a product from here, everybody, and again, please don't take this as a mechanism. I'm not writing a mechanism here, I'm just showing you some idea. So yeah, we should definitely expect this product, agreed? But should we also expect a product from there? The answer is, before you have a misconception, please, no. No. Benzene ring, the ring is so stable, it's not going to give you a product by deconstructing the benzene ring itself. Allylic, we saw products, right? Great. You can't do that with benzene because benzene is so extra stable. It's helping us delocalize the electron and make the radical stable, but it's not going to give you a product because by doing so, it's not benzene anymore. So it's going from high stability to low stability. Make sense, everybody? Sure? So don't break a benzene ring ever, actually, because they're highly stable. So that's the reason I brought up this example. Now to address your question, I think what you're asking me, let me know if I'm wrong. There is a difference between this free radical that free radical. Huge difference. What is the difference? They're both carbons, both this carbon and the other carbon are sp2 hybridized. Absolutely. However, where does that live? In this radical, which orbital does the electron live in? Where does it live here?
In an
Not there. Not in the unhybridized p orbital. Because please remember, which orbital is being used for the sigma bond?
an SP,
It's sp2 hybridized.
SP2 hybrid.
Agreed?
Yep.
Which orbital is being used for that sigma bond? But there's a pi bond. Which orbital is being used for the pi bond?
Unhybridized P,
So where does that live? Exactly.
the S orbital.
No s orbital. There's no s orbital there for carbon. The hybrid sp2. Not the same thing. This is stable enough to exist. That is extremely unstable. So do you see the difference
Yeah.
between the two? Okay. Guys, are we okay so far? Yes?
Yeah.
Yes? Okay. So that is, I think I've covered it all. Yeah. That is the free radical halogenation reaction of alkanes or cycloalkanes. We must be able to figure out products. We must be able to determine the major product. We must be able to write mechanisms to show the formation of the product or products, as the case might be. So, any questions on any of these aspects of this reaction? Okay, then let's go to the next part. One more. Okay. Let's take this as an example. Let's say I'm brominating it, meaning I'm reacting it with bromine, with heat or light. How many products do you expect? Two.
2 products.
What would those 2 products be?
On either sp free hybridized
Absolutely.
bond.
Carbons. Absolutely.
Carbons.
Do you agree?
Yeah.
Which do you expect to be major?
The second one.
Absolutely, because it's coming from the more stable free radical, and maybe, and I'm making up numbers here, we might get 30% of this and 70% of that product. That's a made up number just to give us an idea that that's a major product. Agreed? Now there is another reagent, that is used in syntheses to put a bromine on one specific position that is way better than this. And that's what you were referring to earlier, Carter, and that is called NBS. It also needs heat or light. It is also a free radical mechanism, although we are not going to write it. It's also a free radical mechanism. Now please, let's first figure out what is NBS. NBS stands for, and here are some things, yes, you do have to memorize, or you just use it so many times that you remember. NBS stands for N-bromosuccinimide. Oh, you're laughing at that. Wait, you're going to have many more as we go. Anyway, I'm just kidding. N-bromosuccinimide, NBS. Its structure is that. It's a great reagent, really good reagent. When you heat or light, it's this bond that homolytically breaks, and it provides, there are some medications that are called slow release. What does that mean? When you take it, they go in your system, but they release the active ingredient slowly. This is kind of slow release bromine producing reagent. It produces bromine atoms, but slowly. Not like Br2, this disintegrates or dissociates at a slower pace. So there's never a very huge concentration of bromine atoms in your reaction system. There's always a small concentration there.
Last longer?
Sorry?
Last longer?
Yeah, lasts longer, good. And because it lasts longer, or rather always goes through slowly, it's able to give us this in almost 100%. Almost 90 to 100%. Very high yields of the benzylic product. So NBS is used. This is only for bromine. It is used to brominate, put a bromine in allylic position. You can also do it for that when it just goes specifically to the allylic position, or benzylic position. And it's used very commonly in synthesis because of its higher degree of percent yields for those positions in the molecule. So yes, please make a note. NBS, same mechanism in terms of being a free radical chemistry, but it's more specific for benzylic bromination or allylic bromination. Are we okay so far, everybody? Yes? Cool. I think now this topic, the free radical halogenation of alkanes or cycloalkanes, is done. Let's move on to the next topic. What is the next topic? Oh, we can also, I think I said that. We can also make alkyl halides from alkenes and alcohols, but we will cover them more in chapter 11. Is that right? Did I say that?
Yes.
I think you
Monday?
mentioned.
Okay. So we saw on Monday, I think I wrote this, please let me know if I wrote, if I didn't, let me know, but what did I say? Alkanes, cycloalkanes. Give us that, that's what we've explored so far. And did we say that alkenes can also be used to produce alkyl halides? And then alcohols, am I right? Okay. We will of course study these reactions in a lot of detail next chapter. Chapter 11 is one of the longest chapters because there's so much in there. So we will of course focus on these more then, but just FYI, you will use HX to convert an alkene into an alkyl halide. It's an addition reaction. Do you guys remember addition reaction?
Add something on.
On the pi bond.
Yep.
Right? And alcohols can be converted into an alkyl halides by using one of three possible reagents. You can use HX also, whatever, HCl, HI, HBr, in that, or we can use something called thionyl chloride, which is SOCl2, or we can use PBr3, phosphorus tribal. So, or, not all three of them, one of them. And what kind of a reaction would this be? Alcohol becoming alkyl halide. What kind of reaction is that?
Substitution.
It is a substitution reaction,
Substitution.
absolutely. So we look at the details of how and regioselectivity, see all of that next chapter. We are not there yet, but just FYI, you can do this, you can do that as well.
What's the name of the new topic?
Oh, the new topic, chapter 11?
Oh, it's chapter 11?
Oh,
What
no,
we're
no,
doing?
No. Oh, you mean new topic here?
Yeah.
Really no topic yet.
Oh.
This is, I'm still in synthesis of alkyl halides, right? There are three possible ways to make that.
Okay.
This one we've learned in chapter 10. The other two we'll go into details later. Okay, the new topic, if you will, oh shoot, is it okay for me to erase? Is that okay, everybody? The new topic, if you will, would then be, I think so, yep, reactions of alkyl halides. Sure, we can make an alkyl halide, but what are the different things alkyl halides can be used for? What are the different reactions alkyl halides can go through and give us other compounds, other families? So that's the next topic. Where's my blue? Okay. Alkyl halides. Now, chapter 11, we are going to focus a lot on this because the two most important reactions of alkyl halides, example, let's say if you have, I can convert this into whatever nucleophile is. So what would that be? Substitution, addition, elimination, or rearrangement?
What
kind of
substitution?
reaction? So we will explore a lot. This is one of the most important mechanisms in the entire course. We'll spend a lot of time on this.
Substitution?
Substitution of alkyl halides, of these guys. And the other reaction that also we will spend time on, decent amount of time on next chapter. Can you tell me what kind of reaction is this? Addition, substitutions, elimination, rearrangement. Really?
Elimination.
The skeleton didn't change?
Elimination.
We eliminated Cl and H, produced a pi bond. This is an elimination reaction. We will spend a lot of time on this as well. Both of these is really the focus of chapter 11, is both of those. So alkyl halides will come back soon. Okay, as far as some things we can talk about for now, for here, is what do you think an organometallic means?
Organic metal.
Exactly, that's basically is. Have you guys seen the structure of hemoglobin? No? Hemoglobin is huge because it has a lot of proteins and all of that. How about the heme part of it? What is hemoglobin made of? Primarily speaking, I'm not talking about all the amino acids and all the sugars. I'm really talking about the heme part. Does anybody know? All of that. That's all of that part. What about the heme part? Why do you take iron supplements? Why is iron so important for us? Because it gives you more what? That is it. That is it. What is hemoglobin used for? It is one, and again, I'm not a biology person, so I might be using terms either very loosely or sometimes maybe not even absolutely correctly. So please don't say that to Ricky. But the point is, what's the purpose of hemoglobin? Isn't it to help us carry oxygen through the bloodstream to different parts of the body? That's how I see it. And that's why we need iron, because iron coordinates with the oxygen. Coordinates means it connects somehow with the oxygen that then helps us carry through out your body in the bloodstream. But what is heme? What is it made of? It's made of a bunch of carbons and hydrogens and nitrogens and blah, blah, blah. But what sits in the middle? Iron. It's an organometallic reagent. It's something that is created with organic stuff and a metal. Those are called organometallics. Our bodies have a lot of organometallic things in, which do a bunch of different. Why do we need to take sodium? Why do we need potassium? Why do we? Oh no, potassium, sodium is different because they're that ion. What is it called? Ion transfer circuits or whatever they're called. Again, don't tell Ricky, please, because he'll come and say, but why did you say? I don't know, I'm not a biology person. But the point is,
He kind of does the same thing for chemistry.
perfect, and we fight with each other. You said this. No, but coming back though, the point is there are a lot of organometallics in physiological systems for different purposes, but in chemistry, if I step away from the dangerous zone and come to the zone that I know more of, a lot of organometallic things are used for syntheses of things. Catalysts, a lot of catalysts that are used in organic reactions, organic syntheses, industrially or academically, are organometallic compounds. Meaning something that is organic, carbon, hydrogen, nitrogen, oxygen, blah, 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 and a metal. So we are not looking at all the different possibilities. In fact, that was one of the areas of my research in grad school was creating an organometallic catalyst for a specific reaction, which most of it I don't remember because it was 30 years ago. But we are only going to look at two in this entire course. The two organometallic reagents that the book is introducing us to. One of them, in fact, you will use in lab and also make in lab if everything goes right. We should also synthesize that in lab. So one of them is called Grignard's reagent. Reagent means something you use to do a reaction. That's what the word reagent implies. It's a reactant. Basically, it's a reactant because without that, the reaction won't go. So there's Grignard reagent, which is the same, similar ones are organo, so to speak, organo sodium or organo lithium. These are the common ones used. So how do we represent Grignard reagent? Grignard reagent is R That's our organic. R, magnesium halogen, RMGX, organomagnesium halide. Please notice, organomagnesium halide is Grignard reagent.
So it's always going to be magnesium.
Yes, for Grignards it's always magnesium. And that's the one we will make in lab and use in lab also. Organosodium basically is our sodium or our lithium. Another one that we will also talk about, and this chapter is introducing us to, is commonly called Gilman's reagent. One of the things you will also notice in Ochem is that us organic chemists want our names to live forever. So if you develop something, you give it your name, so it lives forever. Gilman's reagent. Okay, what is it?
Sumita's reagent.
I'm out of that game. What is Gilman's reagent? Gilman's reagent is nothing but dialkyl. What does that mean, dialkyl? R2, two of them, copper, lithium. It's lithium dialkyl cuprate. Lithium is just a counter ion. The actual ingredient is the dialkyl cuprate part. But again, I'm just introducing these things to us at the moment. Now, what is the purpose of these organometallic reagents? So let's pause. You don't have to write all this, it's better to just understand. Look at where carbon is in the periodic table, right? Now, in organic chemistry, what is carbon typically bonded to? Okay, is that a polar bond?
It's non-polar.
Okay, what else is typically in organic chemistry carbon bonded to? Okay, what else?
Carbon.
Well, okay, sure, absolutely. Nitrogen, what else? Maybe one of the halogens, right?
Yes.
Those are the typical ones. Now, those are non-polar, agreed?
Yes.
These can be somewhat polar. What is the electron density? How do I say this? What is the direction of the polarity?
Towards the electronegative level.
Right? So what does that make the carbons? Electrophilic or nucleophilic? Electron rich or electron poor?
Electron poor.
If the polarity is in the direction of oxygen, that's negative. Carbon is positive, isn't that right? So what kind of carbons are these? Are they electrophilic carbons or nucleophilic carbons?
Electrophilic?
So what kind of things will react with that carbon atom? Isn't that right? Exactly. Isn't that right? A nucleophile, something that's electron rich, will go to these carbons because they are electron poor. Am I right?
Mm-hmm.
What if I'm doing a synthesis and I need a carbon atom that's actually electron rich? These won't help me. What has to be bonded to the carbon to make it electron rich? A metal.
A metal.
Because metals all have lower electronegativity than carbon. Isn't that right?
Yep.
Here is your carbon with its electronegativity. Here is lithium, here is sodium, here is magnesium. Way less electronegative compared to carbon. So if there's a metal connected to carbon, where are the electrons going? Are they going to the metal or are they going to the carbon?
They're going to go to carbon.
That creates an electron-rich carbon. A carbon that's the only way we can create a carbon that can now act as a nucleophile for reactions where
Ionic?
we need one. Not ionic, no.
No.
By the way, a magnesium carbon bond has substantial covalent character. Of course, so far in Gen Chem we see metal O ionic, but that's really not the case. Copper carbon bond has a substantial organic character. However, the important part is, so don't go ionic, don't think ionic. Instead think, oh, that is electron rich. Because this is way less electronegative. That's the more important thing.
Is that Mg?
It can be any metal.
Oh,
I
any
meant
metal. Oh, that's right. That's right.
Oh, sorry. Okay.
Yeah.
I meant metal. Any metal. In fact, all metals. Do you guys agree?
Mm-hmm.
Everybody. And that's why synthetically organometallic reagents are so important to us, that, because those are the only ways we can get a nucleophilic carbon for a lot of reactions we will study. Actually, in our future chapters, we will study those. So the question is, we are not looking at the reactions of the organometallic reagents. What we are looking at, though, is how do we make them? And that's what you will also do in lab a few weeks later. How do we make these reagents? All of these reagents come from alkyl halides. That's why alkyl halides. If I react an alkyl halide with magnesium, just metal, magnesium metal, period, it inserts itself between the RX bond and produces Grignard's reagent. Can someone tell me what will be? Oh, no, that's a different reaction. I'm so sorry. That's a different reaction. You guys okay? Yeah. I can just take an alkyl halide, just add sodium, metal, produces an organosodium compound, and of course, you'll need 2 equivalents of sodium so that you can get a byproduct, which is precipitated. Or I can use alkyl lithium with alkyl halide with 2 equivalents of lithium, produces organolithium and alkyl lithium and byproduct. But they are coming from alkyl halides, please look. And how do you get the Gilman reagent? Well, the Gilman reagent actually comes from this guy. Once you get the alkyl lithium, we react it with copper halide, copper 1 halide, cuprous halide. And that creates, of course, this stoichiometry you guys can work out. I'm not doing stoichiometry here, but it creates the Gilman's reagent. The point is, alkyl halides, organohalides, are the source of these very important reagents in organic chemistry. These 4, these are the only ones we will look at, by the way. Are we good, everybody, so far? Yes. Were you going to say something?
No, I was.
I didn't work out the stoichiometry there, because if you're going to work out the stoichiometry, you need 2 of, okay, maybe I can say half an equivalent of this. Because you have 1 equivalent there.